Now it's time to look at some wave reflections. Now what happens when waves change speed? And I'm going to give an example here for waves on a string. So here is some wave, it's just a sort of a wiggly thing, and it's traveling in this direction. I'm going to let this animation loose and let you know that at this point here, the density of the string changes. So imagine tying a thin string to a thick string, or have two guitar strings of different densities or different weights and stick them together and see what happens. So the wave travels along, and when it changes from one medium to another, we get some transmission and some reflection. We see that on this side the wave has become shorter, so the wavelength is reduced, and on this side it's the same wavelength that we had originally, and some of the energy is reflected and some of the energy is transmitted. The parameters are used for this animation. So at x equals 40, that's where we have a change of density. The density in fact increases by a factor of 4. Now something you want to maybe notice here is that if we look at where this big peak is, as we hit the wall and look at the reflection, this big peak is now pointing down. So the reflected wave has a phase change of pi. It's 180 degrees. Phase change is upside down, in other words. But the wave that's transmitted has no phase change. What if we go the other way? So we start with a density of 4 and go to a density of 1. So we start off like this, hits the interface. We see now on reflection there is no phase change, so the big peak is still pointing up, and the other side the big peak is also pointing up. So we have the transmitted wave being faster now because it's in a lower density medium, and there is no phase change. So this is what we do if we just simulate this numerically. In fact, we can write down analytic solutions for how the wavelength and the amplitude of the wave change across the boundary. If we define this is the amplitude, the wavelength is the distance between the peaks, and some initial velocity, then on reflection the velocity on this side is the same, so v1 just in the opposite direction. We have some reflected wavelengths, some reflected amplitude. On the other side we have v2, so a different velocity. We have a transmitted amplitude and a transmitted wavelength. The equations for waves at this boundary go like this. The ratio of the reflected amplitude to the incident amplitude is given by this ratio of the velocities. The ratio of the transmitted amplitude to the incident amplitude is given by this ratio of the velocities. For the wavelengths, the reflected wavelength is the same as the incident wavelength because it's not changing medium. It's going from it's not changing strings. It's just staying in a string of the same density, or changing or staying. For wavelengths, we have that the reflected wavelength is the same as the incident wavelength, which makes sense because it's staying in the same medium. It's staying on the same piece of string with the same linear density, or it's staying in the same gas, or whatever it is, depending on the wave. The transmitted wavelength is scaled by the ratio of the velocities. The frequency of the wave is unchanged. So when you go from one medium to another, the velocity changes, the wavelength changes, but the frequency of the wave does not change. So I'll make these ideas again when we talk about change in refractive index for light waves. It's the same equations for light, obviously, and when light goes from air to glass, it changes velocity, and this tells you how light behaves at an interface. It becomes a little more complicated when we have angles involved as well, because we can have light coming in at and leaving at different angles.